one more important thing we will need in this course is Fourier transform. Okay. So, lot of descriptions are easier in fact in Fourier transforms with Wave number space. Okay. So, basically waves are there, I mean photon as a wave, and then it is easier to describe that in terms of Fourier modes like creation operator, destruction operator. They are for well in both real space and Fourier space. Fourier space is create a wave of wavelength lambda. Okay, so that is creation operator. So, we need Fourier transforms a lot. So, it is straightforward, but please remember that this is for infinite box. Okay, we did lot of turbulence stuff where box is finite, 2 pi box or box of size L. In field theory is typically we use infinite box. Okay, it's we assume the system size to be really large, okay, and it works well, and yeah, no need to worry about box size L. Okay, and in typically d dimensions is typically 3, but sometimes we will use 4 dimensions as well. Okay, so our dimension is d, but d could be 2, 3, 1, 4, or in fact sometimes is also fractional dimensions. Okay, we will find that. Now, one assumption is that f(x) is a square integrable function. Okay, what does it mean square integrable? So, mod f(x) square dx integral is less than infinity or is finite. So, this is called square integrable. Okay. So, Fourier transform is meaningful or it gives a finite number if your f(x) is square integrable. This is by I am not sure Abel, this formalism of Fourier transform was done by mathematicians, and that is what it is. Okay. So, the definition for infinite box we follow this definition. f(x) is a real space function, f(k) is a Fourier transform. Now, this is what we use, typically I am going to use that f hat for Fourier space. Sometimes of course it is going to become operators, but that is later. Right now we are going to use f(x) to f to be function, real function. Well, f(k) is a complex function, it has a real part and imaginary part. f(x) can also be complex because we are using Schrodinger equation now, so f(x) can be complex. That means real plus imaginary. I do not think of it as an operator right now. So, my definition is the integral dk by 2 pi d. So, this is what you will find this normalization, okay, 2 pi to d and exponential ikx. This is my notation, well sometimes some people write is minus sign there, but well people choose both ways, but I like to prefer plus ikx for inverse transform. So, I am using fk to compute fx. So, this is called inverse transform and I use a plus sign. Okay. So, that is what we will always do that notation. Now, given fx I can compute fk, okay, that will be a minus sign. Now, this derivation I think Schrodinger, well the quantum mechanics also this is standard derivation, but we need these definitions. Okay. So, this you should memorize it, and this 2 pi to the power d is in fx, well basically dk by standard. So, when you write dk you put 2 pi to the power d. So, these go together, okay, and dx has no 1 by 2 power d. Okay. This you might have seen in your quantum courses. Some people write in quantum course dx by root 2 pi in 1d and dk by root 2 pi. 2 pi is distributed among the 2 in 1d, and higher dimension is d by 2 in both, but in field theory it is typically this is the one dk by 2 power d, and that is it. This is the definition and you need to know this all the time. Okay, so, this is a very small slide and I just want to introduce the definition, so that is there is no ambiguity. Okay. So, these are different than what we do it for finite box in turbulence simulations, that was a different part. Okay. Now comes the Green's function, which is slightly complicated. So, Green's function as I said is a critical thing. Okay. Now, you will see some interesting stuff in the slides itself, and I am doing it right now before getting into field theory, because once we have this big well, I mean, I am deriving something, I am just going to say that it has been done in the class before. Okay. And it is important that we know what Green's function is. Okay. And this again has been done in your courses before, but let us get this idea very, very clear. Green's function is basically the most important concept of field theory.